Hello, everyone. This is our group presentation for CIS 4321 about car MSRP prediction using multiple linear regression analysis. My name is Bishoy Sadek.
My name is Charlene Lee.
Shalto.
And my name is Somar Dekek.
Okay, so the problems for most of the car manufacturers is to find a balance between what consumers want and pricing the particular vehicle. So it is important for them to know which features are best and make the manufacturer suggest retail price, and which features largely determine the price of the car, and how to produce and sell cars that meet market demands for its target consumers group. So the purpose of our group project is to figure out what features have an influence on a vehicle's MSRP in the car features and MSRP dataset, and we'll be able to know what features are most important to consumers by predicting an appropriate MSRP given a specific set of features, and we'll also be able to understand how those features affect the MSRP the most. Next slide. For data collection, we found our data set on Kaggle, but we could not find the real source of the set. However, all the records were collected from Twitter and Edmunds. Our data set has 16 variables, which are divided to 8 numerical and 8 categorical variables. The numerical variables are year, engine HP, engine cylinder, number of doors, highway MPG, city MPG, popularity, and MSRP. The categorical variables are make, model, engine fuel type, transmission type, driven wheels, market category, vehicle size, and vehicle style. We transfer some of our categorical types to dummy variables. Next slide. So here are all our 16 variables description. However, for our data analyze, we exclude the variables make, model, market category, and popularity. Next slide.
So the next step from there was to describe and clean the data set. The first thing that we wanted to do was to remove all of the duplicate and null or empty values. So this chart here shows all the greens are unique original values and all the reds are null values. Now, if you take a look at engine horsepower, engine cylinders, you can see a couple of null values spread throughout. There were a total of around 100 null values that were removed. However, if you take a look at the market category column, you can see it's almost an entire column of red, meaning it's almost all null. So if we removed all of the values from that column, we would lose a large chunk of our data set. So what we decided to do instead was to remove the market category column itself. That way we can keep all of our row values and not disturb our data set too much, also having accurate results. Next slide. After that, we took a look at outliers. So if you take a look on the left, this is what the box plot for one of our columns horsepower looked like. We had a very small, we had a very high average of the high standard deviations with our three quartiles being very, very slim and a huge number of outliers on the right side. So after removing the outliers from all of our columns, everything started to look a bit more normal, as you can see on the right. Our box plot showed a healthier average with a smaller standard deviation, meaning our predictions are going to be much more accurate as all the data is closer to one another. Next slide, please. Now, as already mentioned, we made dummies for many of our categorical variables. However, this resulted in a large number of columns, many of them having little to no correlation with our target variable MSRP. So what we decided to do from there was reduce the number of columns, only use the ones that are important for our prediction model. Next slide, please. After running our regression model selector, these are the 8 columns that we ended up with. They are year, horsepower, fuel type flex fuel unleaded, fuel type premium unleaded recommended, and fuel type regular unleaded, followed by transmission type manual, rear wheel drive, vehicle size compact. And as we can see, all of these columns are highly correlated, positive or negative, with MSRP, which will help create accurate predictions for our model. Next slide.
For our data analysis, we use multiple linear regression to predict one variable based on the known information about other variables and examine how multiple independent variables are related to one dependent variable. We used recursive model elimination to compare models with different sizes and selected model 8 with highest adjusted R-squared of 0.75. We compared the performance of the model using the training and test sets. Next slide, please. Here are the coefficients for model 8. Next slide, please. For our analysis, we were able to predict a car's MSRP with a given set of features. We also concluded that the RF is not the best model to predict a car's MSRP based on the 75% accuracy that the RFE method yielded. We were able to accurately predict a car's MSRP after plugging in values for the features listed in Model 8. And on the right side, we have the values that we plugged in. Next slide, please. At 75% accuracy in predicting MSRP, manufacturers can adjust features and specs according to the preferred MSRP, budget early on, decide on how to market the car, and have a better understanding and control of the factors contributing to the MSRP. Next slide, please. The limitations include the lack of numerical variables, unknown values which need to be dropped individually, and irrelevant variables such as market category, vehicle style, and popularity. Next slide, please. In the future, we hope to improve our results with a data set that has more complete data and more relevant variables, and use a different model for our prediction. Next slide.
And for our extra credit portion of the project, we chose classification. And the problem that we chose to solve was failing a missing engine cylinder value on a car shopping website. So we assumed that when a shopper is looking for a car or listing a car on a car shopping website, the shopper would miss the engine cylinder value. So the website would automatically use classification to fill and predict that value based on the other features or other values that the user has inputted. The approach that we used was to use 3 different binary classification methods to solve the problem and then pick the best method. The methods that we chose were decision tree, random forest, and naive Bayes. All methods yielded impressive classification abilities of 97% and above accuracy scores. And this is a drawing of the decision tree that we made. And as we can see that the decision tree looks really busy and it's difficult to understand, as well as it might raise some overfitting concerns. So to get a better view of the tree, as well as improve the results, we had to prune the tree. And this is a drawing of the pruned tree. We had to limit the depth of the tree, as well as setting the minimum and the maximum number of splits. Now the tree looks cleaner and it performed better than the original tree. And this table compares all models that we used. On the left here, we have the decision tree model. This is the original tree, this is the prune tree, and then we used random forest, naive Bayes. And as we can see that the accuracy score for all of them is pretty high. They all have 98% accuracy, but random forest only has 97, which is still high. And we just plotted all 3 methods on an ROC curve plot. And here we have the plotted probability of each method and its ability to predict and classify the independent variable. The methods again performed very well. However, naive Bayes showed a slight advantage compared to the other methods. And that's it. Thank you.